Today we're going to continue our work in Chapter 9, Chemical Reactions. If you can recall, for the past week we have been working with learning goal number 1. The students will be able to write and balance chemical equations. We are now ready to focus on learning goal 2. The students will be able to predict products of a chemical reaction. Section 9.2 talks about classifying chemical reactions. This will help us with learning goal number 2, where the students again will be able to predict products of a chemical reaction. The objectives for this section, classifying the types of chemical reactions and identifying the characteristics of different classes of chemical reactions, are 2 skills necessary for students to attain learning goal number 2, where again the students will be able to predict the products of a chemical reaction. There are 5 types of chemical reactions listed on the screen. There are synthesis reactions, combustion reactions, decomposition reactions, single and double replacement reactions. Chemists classify reactions in order to organize the many types. Today we will be focusing on the first 2 types of reactions, the synthesis reaction and the combustion reaction. Let's take a look at synthesis reactions. By definition, a synthesis reaction is a reaction in which 2 or more substances react to produce a single product. Again, a reaction in which 2 or more substances react to form a single product is a synthesis reaction. Let's take a look at the first example synthesis reaction on the board. Reactant A plus reactant B yields product AB. Again, a single product, a single compound on the right side of the yield sign. If we take a look at the second example synthesis reaction, solid carbon plus oxygen gas yields carbon dioxide gas. Again, we only show one substance, one product on the right side of the yield sign. That is how we tell the difference between a synthesis reaction and any other type of reaction. One product will always be a synthesis reaction. There are a couple of rules that we have to follow when predicting products for synthesis reactions, and they're listed here on the bottom of the page and also on the rear of your gold sheet to help you predict products for synthesis reactions. Let's take a look at rule number 1 for predicting products of synthesis reactions. An element plus an element will always yield a binary compound. Again, rule 1 for dealing with synthesis reactions is that an element plus an element will always yield a binary compound. In this example, we have the single element sulfur plus the single element aluminum, and the only thing that they could possibly form would be yielding aluminum sulfide. The only thing left for us to do is to write out and balance the equation. We've got aluminum, which we know is a metal, a solid, plus sulfur, also a solid, and they would need to form aluminum sulfide, a binary compound. Remember, when writing the formulas for compounds, we have to balance charges. Aluminum would be a 3 plus charge, sulfur would be a 2 minus charge, so our formula would be Al2S3. Let's get rid of the charges, since they're not supposed to be there. Compounds are neutral. And the last thing we need to do is balance the equation. We've got 2 aluminums in the products, so we need to add a 2 as a coefficient. And we've got 3 sulfurs in the products, so we need to add a 3 as a coefficient. Again, we know that this is a synthesis reaction because there is only one product. And because the 2 reactants are an element plus an element, we have to yield a binary compound. If we look at the second example, Again, it is sodium plus chlorine, both single elements. The only thing that they can yield are a binary compound product, sodium chloride. The only thing, again, we need to do is write out and balance the equation. Sodium, a metal, would be a solid, plus chlorine, we need to remember our diatomics, also a gas, would yield sodium chloride. Balancing the charges, it's NaCl, a 1 plus 1 minus charge. And the last thing we would need to do is balance this equation. 2 chlorines in the reactants, we need 2 in the products. Changing our sodiums, we need 2 in the reactants. Again, the reason we know that this is a synthesis reaction is because there is only one product. Let's move on to Rule 2 when dealing with predicting products for synthesis reactions. Rule 2 states that a metallic oxide plus water will always yield a base or something that ends in hydroxide. Let's take a closer look at Rule 2. Rule 2 again says a metallic oxide plus water will always yield a base or something that ends in hydroxide. Some of you may be wondering, what is a metallic oxide? Well, a metallic oxide is a metal combined with oxygen, like sodium oxide. Sodium being the metal, oxygen being the oxide, okay? Whenever added to water, it's going to yield a base. So sodium oxide plus water would yield a hydroxide. And the only other element other than oxygen and hydrogen in this equation would be sodium. So our product would need to be sodium hydroxide. The only thing left for us to do is to write this out and balance. Sodium oxide, Na, it's got a 1 plus charge. Oxygen with a 2 minus charge, Na2O. Plus water, H2O, yields sodium hydroxide, NaOH. 1 plus 1 minus charge, match made in heaven, water would be a liquid. The last thing we need to do is balance. I believe we need a 2 here, and I think that will do it. There are 2 oxygens in the reactants, 2 in the products, 2 hydrogens in the reactants, 2 hydrogens in the products, and we balanced our sodiums. Again, this is a this is a synthesis reaction because there is only one product. Lastly, let's take a look at rule number 3. A non-metallic oxide plus water will always yield an acid. So rule number 3 when predicting products for synthesis reactions is that a non-metallic oxide plus water will always yield an acid. Let's take a closer look at Rule 3. A non-metallic oxide, very simple, is a non-metal plus oxygen. Sulfur trioxide, sulfur is the non-metal, oxygen is the oxide part. Let's go ahead and write this out. We've got sulfur trioxide, SO3, a non-metallic oxide, sulfur's a non-metal, plus water will always yield an acid. We know that acids always start with H. We also know there's a list of acids on the front of our gold sheet. Let's look at that list of acids. If we take a look at sulfur trioxide and water, they have a total of 4 oxygens. So the most likely acid for us to form here would be sulfuric acid, H2SO4, to account for the 4 oxygens. And if we take a look here, I believe that's balanced. 1 sulfur, 4 oxygens, 4 oxygens, 2 hydrogens, 2 hydrogens, and we know that this is a synthesis reaction because we only have one product. And again, we have to abide by the rules. The second type of reaction we want to look at today is a combustion reaction. Combustion means burning. Anytime something burns in nature, we have to add oxygen. So if we take a look at the definition for a combustion reaction, it's a reaction in which oxygen combines with a substance and releases energy in the form of heat and light. Again, oxygen combines with a substance and releases energy in the form of heat and light. If we take a look at the example combustion reactions shown, the first one, we've got magnesium plus oxygen gas yields magnesium oxide. We know it's a combustion reaction because oxygen is one of the reactants. It does say here that energy is added in a combustion reaction. We have to add a triangle over the arrow. If we look at the second reaction, we've got sodium plus oxygen yields sodium oxide. Again, this is a combustion reaction because oxygen is shown as a reactant. And again, energy, we need that triangle over the arrow because energy is added in a combustion reaction. Some of you may be wondering, can these also be classified as synthesis reactions because of the one product? And my answer to you is yes, they could, but we'll also classify them as combustion because oxygen is one of the reactants. The last thing we have to look at is a special type of combustion, combustion of a hydrocarbon. A hydrocarbon, by definition, is exactly what it says. Any compound combining only hydrogen and carbon, and they should always be written as gases. If we take a look here, this CXHY is a hydrocarbon. It contains only hydrogen and carbon, and it's being combusted to form, it's being combusted or combined with oxygen gas. It says here combustion of a hydrocarbon always produces carbon dioxide gas and water vapor. This is very, very simple. Let's take a look at the example E. We've got methane, CH4, which is a hydrocarbon. It only contains hydrogen and carbon. It should be written as a gas. It is being combusted or combined with oxygen, also a gas. We need to add energy in a combustion reaction. And we know who the products are because when a combustion of a hydrocarbon occurs, it will always produce carbon dioxide gas and water vapor. Carbon dioxide gas plus water vapor, which is also a gas. And the last thing we need to do is balance this equation. We've got one carbon, we're good. We've got 4 hydrogens. We need a 2 to add 4 hydrogens. And the last thing is the oxygens. 2 and another 2 is 4 on the product side, so a 2 here will balance. Again, we knew that the products would be carbon dioxide and water vapor because we were combusting a hydrocarbon. Hopefully that makes sense. And again, this is our example of a combustion reaction because we had oxygen in the reactants.